Lesson 3, ready, set, go. In our ready problem, number 1, we have a table. Now that table can also be called an input-output table. The first row, the n values are the inputs. The second row are the outputs. So when we're asked on part A to find f of 5, right here, that means if the input is 5, what is the output? So we go to 5 and we look straight below it. 12 is the output. F of 9. 9 is the input. Look straight below. 32 is the output. But part C reverses the idea. For part C, it says, we don't know what the input was, but we know that the output is 22. Right here. So we find the output of 22, and the input was n is 7. Part D, the output is -3. That's here. So the input was 2. Problem number 2, we're just trying it again. The input is 3, the output is 6. The input is 8, the output is -29. The output is -1, the input is 4. The output is -43, the input is 10. Number 3, in the first table of values, how does n differ from f of n? In other words, what do n and f of n mean? Well, n is the input, f of n is the output of function f. Number 4, if you have a table of values like those above, and you can find the value of f of n, how would you go about finding the value of f of n minus 1? How do f of n and f of n minus 1 compare to each other? Well, n minus 1 means the previous input. So therefore, what would f of n minus 1 mean compared to f of n? Well, somewhere along the line, you're going to have f of n, and coming right before it was f of n minus 1. So this is the previous output. Now we go into our set. For problems 5 to 8, create the missing equation for the sequence based on the table, the description, or the given equation. Then decide which equation will help find the missing term of the sequence most efficiently. Efficiently means quickly, easily, without much effort. Then find the term and explain your choice. So they're giving us the recursive function in number 5. It says, now is previous term plus 3. And you can see that here in the table. So to get to the next term, you add 3. Every time you go to the next part, you add 3. So what would be the missing number? That's right, it's 19. Now the explicit equation. Well, this is going to be based on what we've done in the past. First of all, we would want to look at the repeated number. Okay, it's plus 3 every time. So f of n is, now remember, repeatedly adding is multiplying. So it's 3 times something. Now let's analyze this real quick here. 1 gives you 10. 2 gives you 13. 3 gives you 16. Are 10, 13, and 16, are those multiples of 3? They are not. Multiples of 3 would be 3, 12, 16, and so on. How far off are these from the multiples of 3? Well, they are all one bigger than a multiple of 3. So maybe we have to add 1 to our multiple of 3. Now, how does that relate then to the term value? Well, let's just temporarily put in 1 here. What would we have to add to 1 so that we could multiply it by 3, then add 1, and get 10? Or in other words, what we're really trying to find here is, first of all, how could we get 9? Oops, I just noticed I wrote 3 over here. That was supposed to be 9. This is 9. Well, if you think about it, if we add 2, that becomes 3. 3 times 3 is 9, and then you add 1 and you get 10. So that seems to be working pretty well. What we could do is we could replace this 1 with n. So I'm going to erase that, and we'll put in n plus 2. So how would that look for getting 10? Well, we put in 1 as our input, and then we're going to have 3, 3, 3, and an extra 1. Here's 9, right, plus 1. Or in other words, 9 comes from 3 times 3. We didn't have 3 times 3, so we had to add 2 to the 1 to get 3. The value of the fourth term is 19. Which is easier to do? Was it easier to just count up by 3s or to find 19, or would it be easier to use the formula 3n plus 2 plus 1? Well, I think you'll agree it's easier to just add using the recursive function. All you have to do is take the last number given, 16, add 3 to it, and you're at 19. Easy. Okay, now number 6. A few students were a little confused by the dots. The dots just mean we're too lazy to write out all the numbers in between. So in no way is this 18 and is this 22. That's just not how that works. So what are we doing to a number to get the next number? What do we do to 10 to get 14? Well, don't you just add 4? So the next, let's try that again. So next equals previous plus 4. Now, what's the value of the 50th term? Now, what would be easier, do you think? To start at 14, which is the second number, and to add 4, another, how many times would we need to do that to get to 50? That would be a lot of adding 4s. So isn't it easier then to just take the explicit function, this one right here, multiply by 4, add 6, you have your number. So 4 times 50 plus 6 In a few seconds, we get our answer of 206. So it was easier to use the formula. And the formula or the explicit function. So we saw one where it's easier to use the recursive. We saw another one where it's easier to use the explicit way to do it. Number 7, the value of the second term is 24. The sequence is being doubled. Here's the explicit equation. What would be the recursive? The recursive would be next equals 2 times the previous. That's doubling. Find the value of the third term. So what would be faster? Do you think it would be faster to put 3 into this equation or to double 24? Personally, I think it would be easier just to double 24. So I know the third term is going to be 48. Again, so it would be easier to double 24. The value of the third term is 12. The sequence is being doubled at each step. Here's the recursive equation. What's the explicit? Well, the explicit would have to have an exponent because we're multiplying many times. Let's see if we can count our way back. If the third number is 12, and we doubled to get 12, well, what came before? Wouldn't that have been 6? Half as much? And if you did that one more time, what do you double to get 6? It would have been 3. So the explicit equation comes from multiplying 3 times 2. Now, how many times do you do that? Well, on the first term, you didn't do it at all. On the second term, you did it once. On the third term, you did it twice. So, in other words, it's 1 behind the term number. So, n minus 1. Now, what would be easier to do? To find the value of the 10th term by starting with 3 and multiplying by 2 9 times? Or would it be easier to just do f of 10 is 3 times 2 to the 10 minus 1? Well, I'm picking that one. And that's going to be 3 times 2 to the 9th. Let's see what Siri says. What's 3 times 2 to the 9th power?
It's 1,536.
It's even easier to tell Siri what to do to get the answer. So it seems like when you're just right next door to the next number, it's better to use the recursive function. But if you need to find a number that's far away, then let's use the explicit function. Example. Recall that f of 2 means to replace the value of n with 2 and work the problem to find f of n. The point n f of n would be the location on the coordinate plane where n describes the location along the x-axis and f of n is the height of the graph. Given that f of n equals 3 times 2 to the n and g of n equals 8 times 5 to the n, evaluate the following functions with the indicated values. So f of 5 means to do 3 times 2 to the 5th power. What's 3 times 2 to the 5th power?
The answer is 96.
Okay, g of 0. So go 8 times 5 to the 0 power. And that is actually going to be 8. F of 2 means do 3 times 2 to the second power. That's 3 times 4, that's 12. And g of 3 means do 8 times 5 to the third power. And that's a big number. 8 times 5 to the third power. What is 8 times 5 to the third power?
The answer is 1,000.
Okay. There we go. Now on our last part, the go part. In my class, we only had time to do one of these tables, but it's an input-output table. And how do you generate the numbers? Well, you just do substitution. So 3 times 1 plus 5, that's 3 times 5, that's 8. 3 times 2 plus 5, that's 6 plus 5, that's 11. 3 times 3 plus 5, that's 9 plus 5, that's 14. 3 times 4 plus 5, that's 12 plus 5, that's 17. 3 times 5 plus 5, that's 15 plus 5, that's 20. Notice this. As you go down, it's plus 3. And the equation has a 3 in it. That is not a coincidence. Okay, we'll try to get to at least one of these on a future time. For now, that is the end of our Ready, Set, Go.